So, one key to understanding these problems is to understand what fraction of the job a person can do in so many hours. So, for instance, it takes Kelby 10 hours to prepare the food. So if it takes her 10 hours to prepare the food, in 10 hours, she can do the entire job once. If it takes her 10 hours to prepare the food, in 5 hours, she can do half of the job. If it takes her 10 hours, in 1 hour, she can do 1/10 of the job. If it takes her 10 hours, in T hours, she can do T/10ths of the job. And that's the key. So we let T represent the time it takes them working together. That's the thing we want to find. And Kelby can do T/10ths of the job because she can do the whole thing in 10 hours. In that same amount of time, Natalie can do T/15ths of the job. And we want to find a T where those two add up to one whole job. And so this is our equation. We know previously that we can get rid of fractions by multiplying both sides by the least common denominator, which in this problem is 30, because 30 is the smallest number. It cancels 10 and 15. We distribute the 30 through, it cancels the 10, and we have a 3t here. We distribute the 30 here, and the 30 and the 15 cancel to 2t, and we have 30 here. So we have 5t equals 30, divide both sides by 5, and we have t equals 6 hours. It will take them 6 hours working together to prepare the food. Let's let x represent the speed of the dinghy in still water, which is what we're being asked for. In problems like this, there's a lot of information. There's at least 6 things we need to understand and use and get organized, and so it's traditional maybe to make a chart. And the chart is organized by the idea that the speed, the rate, times the time you travel equals the distance you travel if the units match up. So for instance, 60 miles an hour would be a rate, times 2 hours would be a time, and 60 times 2 would be 120 miles. Now, one thing we have to understand is that at least at small speeds, speeds kind of add up. If you're going downstream in a dinghy that can go X miles an hour in still water, then you take that speed at X and you add on to it the speed of the water. If you're going upstream against the water, your speed would be X minus the speed of the water. So the river's moving at 4 miles an hour. So when you're going downstream, you're doing the speed of the dinghy plus the 4 miles an hour. When you're going upstream, it's the speed of the dinghy minus the 4 miles per hour. So what distances are we going? Well, it's 6 miles upstream and it's 12 miles downstream. Now if rate times time equals distance, then we can solve for time by dividing both sides by rate. And so the time is the distance divided by the rate. And so we can put distance, 6 divided by rate, and distance, 12 divided by rate. And it says the two times are equal to each other. It says in the same time that it takes. So we have 6 over x minus 4 equals 12 over x plus 4. We can cross multiply and set the cross products equal to each other. So we have 6 times x plus 4 equals 12 times x minus 4. Distributing, we have 6x plus 24 equals 12x minus 48. Subtracting 6x from both sides, we get 6x here, adding 48 to both sides. we get 72 here, dividing both sides by 6. We find out that x equals 12. So x was the speed of the dinghy in still water. We have 12 miles per hour. And if we want to check that, we can put in 12 everywhere and see if it makes sense. If we put 12 here, it looks like the rate that we're going with respect to the land is 12 take away 4 or 8. Here, when we're going down, it's 12 plus 4 is 16, so we're going 16 miles an hour in effect when we're going with the water. Putting in a 12 here, we get 6 over 8. That's 3/4 of an hour. Putting in 12 here, we get 12 over 16. That's 3/4 of an hour. So the hours are the same, which we thought. And 8 times 3/4 is 6. And 16 times 3/4 is 12. So 12 miles per hour checks. We've got a proportion here. When we set up a proportion, we get a rational equation, an equation with fractions in it, and that's what we're studying. Proportions are some of the most practical of equations. We can use them often in life because a lot of things in our world are proportional. So we have a sample where there's 150 flash drives, and out of those, 7 are defective. So not all of them, kind of a small proportion of them are defective. So the question is, if our small sample of 150 only had 7 defective, then if we have a batch of 2,700 of them, how many would we expect to be defective? Well, notice defective over total in the sample, defective over total in the batch. We have the same kind of direction. Defective divided by total, defective divided by total. So let's be a little more sophisticated in using x for the unknown. And let's cross multiply 7 times 2,700 equals 150 times x. I'm in no hurry to actually calculate. So x equals 7 times 2,700 divided by 150. You could grab a calculator and do that. I don't feel like it. So I'm going to divide 10 into 2,700 and get 270. And divide 10 into 150 and get 15. Now 15 goes into this once. 15 goes into this. 120. I don't know. I'm not sure, so I better divide. Yeah, that's what I thought, but wasn't sure. So we have 7 times 18 equals x. 7 times 18 is 126. So you would expect 126 defective drives. If you got 7 out of 150, that's the same proportion as 126 out of 270. Of course, you could grab a calculator and do this calculation. It would be a little bit faster.